Hey Ryan, Ryan. Oh, I'm recording now. I should stop. All right. Cool. So here, let's go and get into this. I know we were talking about this dissection of an academic paper before. There are a couple of things throughout this. I'm going to be talking about the different aspects of an academic paper and like what's important in them. Particularly the statistics section, I think, is what's probably going to be the most important here. But just looking ahead of where we're going. So today, dissection of academic paper. As much as we possibly can handle, I would love it if I finish this today, but I'm not 100% sure if I will. I'm going to try. And then epidemiology faces its limits. So has anyone read that? There's a PDF for that, like on. Okay, yeah, on Canvas. So yeah, that's a really good paper to read by a guy named Gary Taubes. Really awesome. I have a whole lecture set about that. There's some really important aspects of it that I want us to understand. And I actually just uploaded the PowerPoints that I'm going to use for that as well. So on Friday, not meeting at all. I will be in this room or like around in like my office or another room. I do expect that you are meeting and working with your groups on that day. Now, I know some of you are meeting earlier in the day because Fridays or whatever, or meet tomorrow, Thursday, whatever you need to do. But I'm giving you this time, so I expect you to actually work. Okay, so it's not really a day off. Does that make sense to everybody? Cool. That day, I want you to read the RCT or read it over the weekend because we're going to open up Monday's class with a quiz on that. And we'll likely do epidemiology faces its limits that day or whatever we finish there. And surveys, we might actually end up getting to that after our first test. So is everyone good with this? I will make a review, like I already have it. I just need to slice out a couple of parts to make sure that it's all good. And then like on Wednesday, we'll finish whatever we haven't finished lecture-wise, and we'll go over the review for the test. Again, it should be relatively easy. At least I think it will be. Then we'll have a work day for all of the groups that are even numbered, and all the odd numbered groups, I'm meeting with them on those days. Everyone good with that? Okay. And then the following Monday will be our first test, which hopefully I'll get that done really quick. Now, here's something I want you to know. This paper right here, your dissection of an academic paper, already talked about what type of paper I want you to pick. So like kind of a randomized control trial, done in humans, preferably like have a control group, have an experimental group, all of that. Here's the day that it's due. It's due on the 6th of March, so be aware of that. It is due that day. So going through this just a little bit more, I'm going to address all of these 12 different points going forward. So hopefully you read this paper. It's not my most cited paper, but it actually got like the most traction out of anything I've ever published because it was a bunch of really like kind of big deal buzzwords across the fitness industry. So CrossFit's a big deal, ketogenic diet's a big deal, all of that. And it was actually the cover of this one academic journal called Sports, which is to me is actually a really funny name for an academic journal. But those are all the human beings that are on it, and like we'll talk about it a little bit more. So before we actually go into that even more, this is to help you write your paper that you're working on in your group together. Like what is in all of these sections? So what's in the abstract, what's in the introduction, methods, results, all of that. Methods, results, discussion, references, so on and so forth. So with the finding academic research, it seems like everyone's good on references and APA, so I'm not really going to cover that at all over the course of this. But here, let's start moving on, looking at the abstract. So what is the abstract? Anybody have a guess? Sophia? Yeah. And like truthfully, if you're in a pinch, if you only read the abstract, it gives you a relatively good sense of what is happening in the study, right? Now, frequently, the abstract doesn't really give you all of the like in particular like nuances, like so the magnitude of research idea that we talked about, like how much do these numbers actually impact anything, that frequently won't show up in the abstract. But if you just really need to know something, like get a general sense of it, like on any of our quizzes, if you're in a pinch, at least read the abstract before you take it, because a lot of times you can answer the questions there. But overall, it's a synopsis. And normally there is a sentence or two given for each section of the paper. So introduction, methods, results, discussion, those are really the only things that are covered within the abstract. So if you look at my abstract, I'm not going to read it to you because it's abundantly boring, right? But here is essentially how it looked. Whenever people publish like research papers, the abstract normally has a word limit, and this one didn't have much of a word limit. Since like I don't know if anyone wants to count this amount of words, but it's a lot. You know, like a lot of times it's like a 200 word limit or something like that. But if we look at it, so adopting a low carbohydrate diet, so on, so forth, so on, that's essentially introducing you to the whole idea of this. So like it's been speculated to like reduce like muscle glycogen levels and like stifle muscle growth and like be good for different types of things. Then going on like here in like just a little bit, the methodology, 12 participants. That's essentially the beginning of the methodology aspect of the abstract. Everyone good with that so far? All right, so like if we're thinking about where the results is happening, where does that begin? What do we think? Like tell me the word. Yeah, like I could definitely see either additionally or DEXA fat mass decreased. Either of those would potentially make sense for where the results aspect. So effectively, like that part of the abstract is telling us what the outcomes of the study were. Right? Everyone good with this so far? Right? Hopefully everyone understands percentages. Like these p-values, you might not understand those yet, but like I'm going to try to explain them to you here very soon. And then limitations, conclusions, and like future directions. So like really not so much like discussion, because a discussion is like a long drawn out, like why our findings were a particular way compared to other individuals. But there, it's normally a just conclusion section. So like what's the concluding statement to wrap all of it up? So a lot of times if I'm in a pinch and I need to know something, I typically just read the last like 2 or 3 sentences in an abstract. Now, is that what a good scientist would do? No, they would read the entire thing. But if I need some information really quickly, that is where I look. So like just kind of letting you know what's going on with that. So the introduction. This, it typically provides like a background, then goes into what's missing, and they use these terms: gap in the research, dearth in the literature, or the current data is scanty. So those, I know, like gap in the research, dearth, and scanty, those might not be words that you use like commonly, but they are commonly used in research to try to make a case for why they are doing what they're doing. Does that make sense to everybody? Right? Hopefully that's reasonable. And then they give some flavor of purpose for like how they're filling a particular knowledge gap. So here I'm gonna draw this, I guess. Should I draw some on this side of the board or the other side? This side? Well, because it's right in front of Sophia. Can y'all see it? It's I mean, like I worry about Ari and Jared over there, but it's you can see you don't need binoculars. So typically, an introduction is supposed to look effectively like this. So you want to start like super broad, like as broad as you can. So like a lot of times if it's like a particular like nutrition study, what they're going to do is say like obesity is a problem, X amount of people are obese in the current like society, whatever, right? Stuff like that. Typically that's what happens. Then they start referencing other papers or like other like research like individuals, right? So like that's that is effectively like the background. This you can increase that size a lot because there's going to be a lot of research. And whenever you're writing your papers, that's really where you're going to be citing the majority of things the first time. Does that make sense to everybody? Right? Then after that, we have the research gap, meaning like within those other papers, there is a particular thing that has not been done to assess or address this really broad problem. And that gap in the research, that's frequently where people say their purpose and then hypothesis. That is effectively how introductions look. Is everyone good with this? Right? I know you're good with it, Ari. Yeah, man. Cool. Gosh. Wow. All right. Moving on. Hopefully all of that makes sense. Like whenever I read introductions, they don't always follow this particular framework, but it's somewhat formulaic. What's up, Trent?
Obviously, if it's in that framework, it's correct. But if there's a couple things switched around, like the hypotheses up at the top, like that's incorrect. I guess it just doesn't flow right. So I'm assuming that you're gonna want us to follow that.
Yeah. If you're being creative in it and it makes sense, that's okay. It's that's one of the hard things with grading writing is that like sometimes you can break the rules and it makes sense, but if like hey, why reinvent the wheel whenever someone already figured it out for you, right? So that's at least that's my assessment on it. Now like I'm into creativity, so if you do something interesting, I'm with it. But like overall, like that's how that goes. So here, hypotheses. Two things I want you to know about them. And in your like papers, you're going to need to address if it's a directional or non-directional hypothesis. So like say in my paper, here were two different ways how I could have had this. So a non-directional hypothesis is I predict that the keto group will be different than the control group. Notice I'm just saying different. I don't say which direction. Yeah, oh yeah, it's super broad. And like most research is actually done this way, right? And and if we talk about statistics, how most statistics are done, they're different for a non-directional versus a directional hypothesis. And just a lot of the time, people who don't know how to do statistics very well, they almost always do the non-directional, like statistic rather than the directional one. Now, in your particular group, I can help you figure that out, like which way that it's going. And a directional hypothesis, this here would be, I predict that the keto group will have less body fat than the control group. Well, here, like I'm gonna draw something up here really quick. Because it's actually a lot harder than you think. I mean, I think it is. So everyone's seen this before. This is just a normal distribution curve, right? So how a non-directional hypothesis works, mostly all of your data is going to be right here, like around the mean. Now, a non-directional hypothesis, whenever we run statistics on it, in order for it to come back statistically significant, it has to be in this region or this region, which is effectively 3 standard deviations from the mean, right? Everyone good with that? That is a non-directional hypothesis. And this will make sense whenever we get into like a p-value of like 0.05, right? So a 0.05 means 2.5% on this side of the mean and 2.5% on this side of the mean. Now, if we have a directional hypothesis, as I'm assuming many of you will, that means I can put that whole 5% on one side. Does that make sense? So like if we like gather a bunch of data on people and like we get a mean for like this group and that group for whatever we're doing. Do you see how it would matter if I had a hypothesis before? So like I don't know, like say here's like one glob of data of like say the control group. And over here I have the glob of like the experimental group. If I have a non-directional hypothesis, meaning that it has to be in there, it's going to come back statistically insignificant, meaning I can't really report that, oh, it had this massive finding. But if I have a directional hypothesis saying that it's going to be above the control group on whatever metric, then right here, checkmate, right? Like now it's statistically significant. Does this make sense to everybody? I'm trying to be as conceptual and non-mathematical as I can with this. So that's overall the biggest difference between a directional and non-directional hypothesis, is how much like wiggle room you have to call something statistically significant, right? Do you think that that might be important in like how we say like this is a big deal or it's not a big deal from a scientific study? Right, like I think so as well. However, many times people don't really pay much attention to it. So here, I already talked about this, like how the introduction works. So I'm sorry I'm backtracking just a little bit. Effectively, this is what I'm talking about in this scenario. So the introduction, it starts broad, it gives specific examples, it points out contradictory findings. So over here, the given specific examples, that's the other papers aspect that I'm talking about right here, points out contradictory findings. That can also be in the other papers. So say this, like my paper, what I showed in particular is that sometimes, like whenever people do a ketogenic or low carbohydrate diet, they don't lose any muscle mass, but other times they do, right? So that's a contradictory finding, and all of that is done in me citing other papers. It's like, oh, so-and-so said whatever, so-and-so, someone else said a different thing, and that actually leads us to, like, the contradictory finding leads us to the gap in the research overall. And the particular topics all of y'all are looking at, you might not have a good dichotomy of like it goes one way or another way. So frequently, the gap in the research is kind of the replication crisis that, hey, we just need to reproduce more of this in a different population or a different set of people. And that's perfectly fine, at least I think it is. Like we'll talk about the file drawer problem and how not so much everyone else thinks that. But that's really all I wanted you to know about that introduction right there. Okay, so in the method section, what is frequently talked about almost first is something called like ethics approval. It said it right there. How did I have a mistake in my head? Because I'm tired. Great. Okay. There's almost always something called the Declaration of Helsinki that's brought up, which is essentially just a large body of individuals saying things that you can and can't do to people scientifically. What was it? Like does anybody know like the Tuskegee experiments or anything like that? Has anyone ever heard of this? I don't think I'm recalling this 100% right. Oh no, not the Tuskegee Airmen. But I'm fairly sure the Tuskegee experiments in like Tuskegee, Alabama, like where I've done a lot of things. Effectively, what they did is they just gave syphilis to like a bunch of black guys to see what happened, and it's just like, okay, can't do that, like that's bad. So at least that's part of it. So we have things called institutional review boards that review if we can do something or not something else. Like I'm not going to talk about that too much because I need to actually look to see if that is correct or not. But I don't know, like we can look at it. Next in the methods, frequently how you obtained the subjects and got their consent. So essentially your recruitment for how you found them. So we'll talk about like different sampling styles. Mostly what people do is a convenient sample. So there's an old joke that the most studied people on the planet are like college students and mice. that like we know everything about them, because in most research, and probably what all of you are going to do, is what's called a convenience sample. So you essentially just obtain friends and people that you know through, you know, however you obtain people. Because there's different types of like random sampling and things, but I'm not going to teach about that too much because I think it's a distraction. Next thing, sometimes give subject characteristics like height, weight, how much they exercise, how much they smoke, how much they eat, what their BMI is, all sorts of things. However, that is frequently done at the very beginning of the results as well. Then, like methodology sections, talk about the study design, what exactly is being done in the study, and like the randomization purpose. The idea here is how you're writing the methods. I could read your methodology section, and then I could do your exact study without talking to you, right? So that's how I'm expecting everyone to write your methods for your group project. Good? That like I can read it and make sense of it and then do it without ever consulting you on how to do it. So it can be relatively long in some cases. Another thing is the instruments and tools used. Frequently, the instruments and tools, you say, like the different bikes that we have in the lab, I would say like a Monarch 894E cycle ergometer made in Stockholm, Sweden. That's frequently what people would say. So that it's like, okay, you know that this is the model of bike I'm using, and this is where it's from, in case there's another bike made somewhere else, which Monarchs are only made in Sweden, so whatever. But that's a particular aspect of it. And like in our animal trial, it explained like quite a bit more in depth that I think you could have just glossed over and it was perfectly fine. The next thing, statistical analysis or analyses. This one, there's almost always a statistical analysis section at the tail end of a methods. Like, so after you get the data from your study design or whatever, how are you statistically going to show that this was an important thing or whatever? So one of the first things that people typically do is set like, well, here, I'll come back to that. No, I'll just go forward because this is important. For statistical analyses, here's one of the biggest things that I want you to know, and it's 100% going to be a question on a test. Two things that always need to be represented. So whenever you see anything, we need to know these. A measure of metal, dude. Cool. Like, are you writing notes on there?
Yeah.
Dude. All right. You're a lot better than I thought, Trent. Oh, sorry. Nothing. I didn't record that. So two things. Back on track, self. Two things. Central tendency and variance. So what are three measures of central tendency that you've been taught in classes before? Hell yes, man. Good. You know what? You make me so happy. I'm sorry, Trent. I'm messing with you, obviously. Right? Crap. Central tendency, mean, median, mode. So typically a mean or an average is what's almost always used. Like most of the time we would only use a median if we had a crazy variance or some type of oddly distributed like data. So here's one big example, income. Almost always we report a median income because some people make like $66 billion a year, right? It's that idea is in my head because Bloomberg, right? Like, I don't know, like I think it said 66 billion is how much he has. So he doesn't make that much a year, but he makes a lot a year or whatever. And me, I make just a little bit less than that. So, right, it's hey, you know what money can't buy you though? I can bench press a lot more than he can. So it's and strangely, I think we're the same height. Like, would y'all vote for someone my height? You would? Okay, only one other time has someone my height won, and it was James Madison, right? And I was actually like an inch taller than him, but it's I was because I was around back then. Back to central tendency. So that would be the case that we would use a median, but overall it's an average. Mode, like that's I've almost never seen that actually reported in an academic paper. I'm sure that there would be a reason for it. I just can't come up with one in my head. Now, variance, this right here, I want everyone to know, range, that's frequently reported whenever we have a large age range. So say if we have a study where people are like 19 or 18, depending on the state, up to 75, then you would report an age range. Like you would report an average age and also an age range in that case. So that's a condition to do range. The other more common one is standard deviation, which is actually, well, that's the most common variance like metric. And how you actually calculate standard deviation is extremely bizarre. But Excel will do it like that, so it's fine. You don't need to know the calculation for it. And there's actually something called standard error, which I'm not going to talk about. That's done more in like in vitro research. Common stats that you will see, a t-test. A t-test. So here's two different kinds that I want you to be aware of. So the first one, has anyone ever heard of t-tests before? Right? Okay. So this is effectively to figure out if something is statistically significant or not. And Excel can do it, and I'm going to show those of you who are in groups doing these statistics how to do it. It's fairly easy. But the two different types that I want you to know, the dependent and independent t-test. So just if we know what those words mean, I think we'll understand what they're actually assessing. So a dependent t-test, that means I'm measuring one group at two different time points. So essentially, that second time point is dependent on the first time point because it's the same person. Does that make sense to everybody? Right? So that would be what we would call like a longitudinal study. Well, kind of, right? Does this make sense to everybody? Well, like say I have all of you and I put you on a ketogenic diet for 12 weeks. Right now I measure how much you weigh. In 12 weeks after the ketogenic diet, I measure how much you weigh. I would then do a dependent t-test, also called a paired t-test, but I'm going to call it a dependent t-test, in order to figure out if those two different time points are statistically different from each other. This next one, an independent t-test. So those of you doing a more like cross-sectional survey type of thing will probably do this. So this is comparing two groups at one time point. So like in here, if I wanted to do like body weight, males versus females, and I measured everyone right now, that would be an independent t-test because how much the males weigh, that has nothing to do with how much the females weigh, right? Because they're independent of each other. Independent samples is what it would be called. So hopefully that makes sense. Some other things that you might see, they're very much like the t-tests. There's something called a ANOVA, which stands for Analysis of Variance. So in particular, one that's done very frequently is called a one-way ANOVA. And it's very similar to the independent t-test, except instead of having two groups, we would have three groups. So that's essentially how an ANOVA would work. Say, like, if in here we only had three different favorite colors, like some of you favorite color is red, other of you blue, other of you green, and then I compared your body weights right now. That would be a one-way ANOVA to compare the body weights of those different groups. Does that make sense? Or is that a stupid example? Hey, like, I don't get paid that much, so like that's what y'all get for coming to Whitewater. It's joking. I like truthfully, I actually like this better than a lot of the bigger universities I've been at. So that's I think it's more fun. Next thing, repeated measures ANOVA. You'll see this quite a bit as well. This is done when you're looking at two or more groups over time. So it's essentially mixing the independent and dependent t-test. So it's a bit of more stringent statistic in order to find differences. Now, one thing to know, I already talked about the normal distribution a little bit. All of these four statistics presume that there's a normal distribution, right? Is everyone good with this? right? So meaning that like most of the people cluster around the mean, and then standard deviations out are less and less individuals. Is everyone good with this? Right? And like I could talk about like um, like not standard deviations, the normal distribution for ever, and I'm not going to. So like typically we're taught that most things are normal distribution, and that's true. But like most really important things are not normally distributed. So like money isn't, for example. So yeah, like talking about Bloomberg, for example, it's like there's not a normal distribution of how money works. That would actually be something called, if you're interested, it's called a Pareto distribution. But I'm not going to test you on that. Next thing, correlations. And I need to go a little bit faster. Correlation, all of this is, if you've had me in other classes, I always talk about correlations because they're fairly fun to run. And I always give the same values for these. So it's just a statistical measure that indicates the extent to which two variables fluctuate or move together. So as one variable goes up, another one goes down, or one goes up, another one goes up. So here, this is a strong negative correlation. It says temperature over on that y-axis and heater sales. So hopefully that makes sense. Like as the temperature goes up, there's like less heater sales, right? Is that right? Yeah, because heater sales are very low right here, and then there's more as the temperature goes down, right? Like, kind of stupid example, but it works. Weak positive correlation, the number of advertisements seen, purchase intention, that goes up just a little bit. Here are some numbers that I want you to know. And like in other classes, I've had people memorize these exact same numbers because I think it's important. So the correlation, it's frequently called a Pearson R, or just an R value. So it ranges from -1 to +1. So a -1 would be something like this strong negative correlation. That's what it would look like. And we can have like a -0.2 to a -0.4, and that would be just a negative relationship, right? So overall, like negative relationships just look like as one goes up, the other one goes down. A positive relationship, both go up together. But here, put positive or negative in front of them, it doesn't really, well, like it does matter, but like the weak, moderate, and strong, that stays about the same. So 0.2 to 0.4, that's typically a weak or small correlation. And 0.4 to 0.6, that's a moderate correlation. Hopefully you all have seen this in my other classes. A 0.6 to 0.8, that is a strong or powerful correlation. And if it's over 0.8, depending on what we're measuring. Some statisticians will say there's not enough variance between these two different things to call them different. So like say if we're measuring some type of like construct on a survey. Like one thing that people talk about a lot. Have y'all ever heard of grit in other classes? Grit, right? So like does everybody know what like the term grit means? Like you have like persistence to like do things and all that type of stuff. So grit, that's a psychological construct that's measured from like a couple of different survey things, right? Now grit has a like 0.9 correlation with a personality metric called conscientiousness. So that is an example of grit and conscientiousness actually aren't different things whenever we measure them. But like I don't know, some like the word grit sounds better and it's easier to spell than conscientiousness. So I think that's why people actually talk about that. But yeah. Okay, moving on. Here, regression, it's very similar to correlation, but it's more about prediction. Like a regression is just called R squared. Everything else on there you don't really need to pay attention to. Those are just bullet points for me to laugh at. Regression, R squared, this is about prediction. It's like you essentially just square what the like Pearson R correlation value is, and then you get how much variance is predicted from like one thing to another thing. Okay. So last thing about statistics and p-values. So p-value, this really just stands for like the probability value. So probability, that's that's what I want you to know about it. It's here, like I'm going to read this to you. Is the measure of how likely a null hypothesis is true. I'm going to show you like what null hypothesis means, like really in depth here in a second. So the hypothesis that there is no significant difference between specified population, any observed difference being due to sampling or experimental error or random chance. So here's the thing, for example. In my study, there was a like body mass group by time interaction, and I got a p-value of 0.053. So what this means, if I get a p-value of 0.053, it means that just due to random sampling error, I would come across with the exact same results in 5.3% of the time. Does that make sense to everybody? Right? So if I ran the study 100 more times, and what I did was just random error, there was no true effect of the ketogenic diet making people lose weight, I should come away with the same results 5.3% of the time. Does that make sense to everybody? So it's essentially the percent that all of this is just due to random noise, right? Or things not really being related. Is everyone good with this? And overall, most scientists and statisticians like kind of agree, even though like a lot of people are against this, that the p-value of 0.05 below that is statistically significant. So we're okay with like a, what would this be? A 1 in 20, that like we would come away with these results 1 in 20 times, that like this is just random error, right? Like that sounds like a good gamble, right? Like if you were like, I don't know, like how people gamble. I don't understand it. But like if you had a 1 in 20 chance of like being wrong and not winning money, you're okay with that. So like a 19 in 20 chance that you're going to be right. That's effectively what this means. Right? Is everyone good with that? I don't think I explained that very well, but just remember, 0.05. Significant stuff. Cool. All right. Like moving on. So whenever I was talking about like null hypothesis testing, here is the biggest thing that I want you to know. So whenever we measure things in studies, like we measure a particular like aspect, or we perceive it, versus reality. So if we measure it that a given thing is true in reality, it's correct, we're all good. But if we measure it and we think it's true, right, but it's false in reality, that is what's termed a type 1 error or a false positive. Everyone good with this? I would know that for a test, right? Next thing, a type 2 error. I measure something scientifically, and it ends up like not being true. However, it is true in reality, that would be a false negative or a type 2 error. So typically how I remember this is just like top right-hand corner is type 1 errors, bottom left-hand corner is type 2 errors. That's how I memorize it. However you want to memorize it is fine with me. Cool, I need to keep on going. Is everyone good with this? Right? All right. And then the p-value is essentially indicating how likely it is to get either a type 1 or type 2 error. So if there's only a 5% chance likelihood that I'm going to get one of these errors, I feel relatively comfortable with that, right? Everyone feels comfortable with this? Good? Okay. It's I know this is a bit like esoteric, but you know, whatever. Now, here's the thing that I'm going to I think this is a big deal. I'm sure a lot of other scientists and researchers do not think that this is a big deal. I want you to know this equation right here. So p-value is equal to 1 minus parenthesis, 1 minus 0.05, comma, to the n power. So here's the thing I want you to pay attention to. Whenever we're talking about these p-values, like the likelihood of something like just being due to random chance or probability, it really depends on how many dependent variables that we have. So here that n stands for the amount of dependent variables, so outcome variables, so like body weight, like how much they could bench press, how, like I don't know, like whatever other variables that we're interested in. All right, we good with this? So in my study, I came away with, I believe like there were 2 things that were statistically significant. So this equation is going to tell me, based on how many dependent variables I had in the study, how likely it is to get something statistically significant that is just due to chance. Is everyone following me on this? Right? Okay, so like looking in the study, right here, these are all the dependent variables that I could count, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 dependent variables in my study. So how we would do this math, we would just put 16 where that n is and run that math. Right? Everyone good with this? Right? Like type it in Google. It figures it out for you. So what I came away with, there is, in my study, there is a 56% chance of at least one variable coming out statistically significant, and it being just due to error, just due to randomness and error. So, like, has anyone like read my study? Right? No? This would be a lot more impactful if you did, because I got about 2 things that were statistically significant, and there was a 56% chance that at least one of them would be, just by flipping a coin, basically, right? Like that's just like how math works. Everyone good with this, right? Okay. So a problem with most scientists is they do not correct for this. Now what I could do is I could alter my p-value and say 0.05 isn't good enough. And I could make it like 0.00001 to make it like really sure that this is statistically significant. But most scientists don't do this, right? So whenever you're reading research, something I want you to be aware of, if they do not correct for multiple hypothesis testing, the likelihood of them getting significant results, or what's called a type 1 error, right? They measure it as true, but in reality it's false, goes up a lot, right? Like that's kind of what I'm trying to get through to you. This would be a lot more interesting if you read this study, but that's okay. That's all right. Cool. It's I just want to make sure y'all are getting like what I'm telling you right now. Okay? So what I'm saying is most of the time whenever research says that they have significant findings, they did not correct for multiple hypotheses, because there's basically never a study that gets published where there's only one hypothesis or one dependent variable, right? So if they don't do this correction, like to the nth power of how many dependent variables that they have, then the likelihood of them getting something that's statistically significant, that is not actually real, that it's just random error, goes up a lot. So
basically, they want more things in there that could possibly go wrong to prove that it's statistically correct.
Yeah. Well. So like, here's the thing. With my study, essentially what I did, I had a bunch of people like doing CrossFit, and I was like, hey, don't eat carbs, right? And I just want to measure what happens. That's basically what happens. So to figure that out, all I have to do is a weighing scale. Weigh them once at the beginning, weigh them once at the end. Why did I measure all of these different variables? to get something significant, right? So there's a term called sample the universe, right? So the more dependent variables that you have, the increased likelihood that something is going to be statistically significant, right? Just because, like, if I get one thing, if I only measure like one thing, there's a pretty low chance that it's going to be statistically significant, right? Because there's only one variable I'm looking at. But like if I'm looking at a bunch of different variables, at least one of them is going to be significant, right? Because like there's so much random noise that's going on all the time. Are y'all good with this? Does this make sense, right? So in a way, whenever you're interpreting scientific research, be more skeptical about things. That's what I'm saying, right? Is everyone good with this? Right? It's I think that that's really alarming. Right? Is that not alarming to anybody? Right? Okay, so hopefully it is. Here, just talking about the results really quick. I know I only have a minute or so, but I think I can get through this. So outcomes after doing the statistics. This is where the findings are reported. Frequently, there are graphs and figures and tables accompanying this section. So like whenever you're writing your results, that's what I expect to see. That this group was different from this group by whatever percentage, and this was our p-value after doing whatever statistic, and like without bias or interpretation. Last thing, and like we'll call it a day. The discussion section. This is essentially the reverse of the introduction. So you start off by being more narrow. It's like an actual pyramid. You recap the findings in your study, and then after recapping the findings in your study, you compare it to other studies. So getting a little bit more broad. And then you talk about like how it adds to whatever scientific field, and then at the end, some limitations and conclusions. And those conclusions being essentially the broadest. Like, how did we deal with this super broad problem? Like, what do our conclusions have to say to that, essentially? Is everyone good with this? Right? Okay. And like overall, they just discuss it. Last thing, there's frequently a conflict of interest. I'll talk about that whenever I go through the paper a little bit more. But that's all I have to say right now. And I expect you all to meet and do things on Friday or Thursday. I'll be around if you need any help. So, cool. Have a good weekend if I don't see you. Hopefully I will, though.